This is just a quick video on the different interpretations of double integrals in the context of, you're given a function of x and y. In this case, it is 1 plus y. This is a problem from the problem set notes on our website. And the idea here is I just want to introduce you to the Mathematica commands called DensityPlot and RegionPlot 3D, which will help us with interpreting double integrals. So we'll kind of take a look at this problem, and the basic idea is that in this particular context, the function of x and y, in this case 1 plus y, has a meaning. And the meaning is that you take a little region of this, a little subregion of this semicircular region, and that little region has some sort of mass. In, I guess, British units, it is slugs per foot squared. So each little region of this subregion of this semicircle has a weight, and the idea is, can we find the total mass of this region? Okay. So to kind of put this problem into context, we have been looking at, say a function of x and y, right? And in this case, the function was 1 plus y, and then our domain D in the xy plane, I believe, was a semicircle. And I think it went from -2 to 2. And so that means that if this is the top half, this is in xy coordinates, this is y is equal to the square root of 4 minus x squared with the positive root. So there's our function. And here is a description of the region D. Okay, so if this had been a problem from a previous section, say 14.2, they would have just asked you to find the double integral of this function f dA over the region D, and you would have maybe chosen the order of integration dy dx, so the function doesn't change. But if we do this as a dy dx problem, y would go from 0 up to y is equal to the square root of 4 minus x squared. So we're just setting up this double integral, and the question then is, if you could compute this, that this has two different interpretations. Okay. The first interpretation is the one that we've kind of been familiar with. We had a function of x and y, and so we know how to, and then again, this is just going to be a sketch. This is probably some sort of plane, right? Well, not probably, it is some sort of plane. Z is equal to 1 plus y. That's y to the first, so this is a plane. And we have some sort of region D here, this semicircular region, and so we're looking at that up on the surface. And again, this is just a sketch, please don't hold me to this. But there's your volume of the region. This double integral will be, quote, like the net volume above this region but below that function. And that is the interpretation that we've been looking at for a little while now. There's another interpretation here that if you interpret 1 plus y as the mass density, I know in the previous problem they used slugs per foot squared, but let's just say we're going to use kilograms per meter squared, for example, right? And then you bring in a dy dx or a dx dy, and that will have the units of meters squared. So you can kind of think of this double integral as something with kilograms per meter squared, and then you put the units of meters squared, and then those units simplify to kilograms, and you are going to be adding up a bunch of kilograms, which is mass. Okay, so what I want to show you in Mathematica now is how to kind of use Mathematica to visualize these two different roots. One, how to visualize the 3D region. That will be important for this interpretation and viewing the double integral as a volume. And then the other one, I want to show you how to view D as just a region in the xy plane, D with mass. And that will be talking about a density plot. So Mathematica has these two commands kind of built in, and let's take a look at that now. Okay, let me switch screens here, bring Mathematica into the problem. Okay. All right, so the first interpretation, well, we're talking about interpreting our function x and y, right? So let's just go ahead and define our function f of x and y once. Okay. And then we're probably, let's do the second interpretation first. So let's call this mass density. I'm just giving this plot a name. And there's this interesting command called DensityPlot. DensityPlot, and let's plot our function f of x and y. And then what you're going to put here after the function is a description of the region D. So we need to describe in these two blanks the region D. Well, D is a region in the xy plane, and it was a semicircle that went from -2 to 2, and the y variable went from 0 up to the square root of 4 minus x squared. Okay. So what we should see here is a 2D plot. We've only got two variables, x and y, f of x and y, and we're going to plot this as a density plot. Shift return, and there is a plot of your region D with colors giving the relative weight at each point. Remember, we've seen the color function before. Let's turn this plot into a plot where the colors make some sort of sense to us. All right, and we can see that here at the bottom of the plate, the weight is lower, and up at the tip, that is a heavier mass density. There's more density at the top here. Okay, so that is your first way to kind of get a visual of this function as a density function. Okay. We, of course, know how to plot this thing as a surface, right? That is just plot 3D. When I say plot this thing, I mean plot the function f of x and y. If you visualize that as a surface, then, and let me just copy and paste this same region. We want to plot this over the same region D. Okay, close the bracket. And there's a plot of our surface. It is a plane, except it's a plane that looks a little bit, it's not so rounded here because we're not plotting this plane over a rectangular region. We are plotting this plane over that sort of semicircle region. Okay, so there is our function, the surface. Okay, well, the next thing we want to do, if we were going the surface route, we would then say that that double integral would have given us a volume. So how do we plot? Sometimes this is very helpful it's hard to visualize the region that you were trying to find the volume of. So Mathematica has a plot here. Let me just kind of demonstrate its use by example. We want our z values. You need to give a description here in this first blank, a description of, so there are three parts to this code. You need to give a region description here. And then here you need to put x bounds, y bounds, and z bounds. And these bounds are the values of x, y, and z that you want to try to put into this function to see if you get a true statement. If you do get a true statement, the computer will light up a pixel. So if we put a region description here, what I mean by that is that we want our z values to be bigger than 0, and you want the z values to be below the function. Right? So we had our function defined above, so I want the z values above 0 but below the function, and I want my y value. So now we're going to go in and describe the region D itself. I want my y value to be less than the top half of the circle. So that's 4 minus x squared. But we also want y to be greater than 0. And that should be enough to describe the region D here. We want the y values to be less than the top half of the circle, but bigger than 0. And then in the z direction, we want to be below this surface, but above the z equals 0 plane. So that should be enough to describe the region. Now you need to give it some x values and kind of just give it a region of space to plot in. So give it a rectangular region. Let's say x goes from -2 to 2. Let's let y go from -2 to 2, and let's let z, although we know z doesn't get negative, let's make z go from, okay, let's let z go from 0 to 3, something like this. Okay. And here's a plot of your 3D region, but it looks, kind of rough around the edges, and that's because this is a very difficult computation to do, and the computer doesn't want to do too much work unless you ask it to. So let's ask it to do a little bit more work. Let's do plot points, and let's make this plot a little bit nicer. Let's up the number of points it should plot to 50. And here's your region taking shape. If you go to 100, it'll take a little bit more time to compute over here. You can see it's taking more time to compute. The fact that that's still grayed out, it also says running up here. But there is a plot of your region. Okay. So if you were to do the double integral that I wrote on the previous page, you would then be finding the volume of this region. Or you would be finding the density, the mass of that region D. Okay. So it's just kind of, in case you're not familiar with this, let's bring all these plots together. If I put semicolons, I've got no plot here because I've got semicolons at the end. Let me bump this down to 50 so it didn't take too long there. And let's just do a graphics grid. Let's see if this will work. So you put all the points here. Let's say mass, density, surface, and volume plot. Let's see if you can put all these together. And there we are. I can make this a little bit bigger. Image size, say 500. Experiment around with the numbers. It should make it a little bit bigger. Or you can just drag the whole thing to make it bigger. Well, maybe. So there's your surface, there's your density plot, and here is your 3D region plot. And that will be the end of the setup of double integrals and their different interpretations.